this is to treat it like we did the sodium chloride problem, just add a step or two that allows us to account for water. Okay? So the first thing we need to do is identify the parts that have to go together in two balanced half reactions, otherwise we can't make them work. Right? So I identify the products and the reactants that have to go together. Right? Basically anything that has non-oxygen or hydrogen. Right? So in this case, the nitrogens have to go together into a half reaction. The bromines have to go together. So my first half reaction is N2O turning into nitrate. And my second half reaction is Br2 turning into Br minus. In the example we did on Wednesday, we didn't have to worry about that second step that says balance all non-HO elements, right? If we don't do that, we can't make the equation balance. In those problems, everything was one-to-one, so we didn't have any problems. But here, our nitrogen is not one-to-one, right? In order to make our nitrogens balance, I've got to put a 2 there. Likewise, for my bromine, because I didn't leave myself enough room to put a 2 in there, I'll rewrite it here. This is an example where we have to make sure that we make those bromines balance. Right? I think the example on the problem set has at least one half reaction that has to go through that step. Right? So keep an eye out for that. After that, we're looking at trying to find ways to make oxygen and hydrogen work based on the involvement of water in our reaction. Now, it's kind of nice in this case, bromine doesn't do anything except for add electrons, kind of like chlorine did. So we don't have to worry about O or H, and I can finish my half reaction for bromine going to bromide just by adding electrons. But our N2O going to nitrate requires that we do all of the steps. Question? So the first thing that we have to do is account then, after we balance nitrogen, account for oxygen by adding water. So as I look at my equation, I've got 6 oxygens on the right-hand side and 1 on the left. So I'm deficient by how many oxygens? I need 5 more oxygens. They have to go on which side? They got to go on the left. So remember, the only ways we're going to be able to do this, at least sequentially, is to start with water. Right? By adding water, we've introduced hydrogen, which we didn't have before, but we have a way to account for that because we have hydrogen ion in water. We simplify it by, instead of saying H3O plus, like we do when we do our KWs and such, we simplify it by saying we can just assume that we can talk about the H plus that's present. So in this case, as I look at this reaction, how many hydrogens do I have on the left? 10, right? Remember, I'm going to multiply by the coefficients. That's what catches people. How many hydrogens do I have on the right? 0. So in order to balance the hydrogen, I have to add 10 H pluses to the right-hand side. And again, because our bromine had no oxygen or hydrogen in that half reaction, we don't have to do those steps, right? There's nothing to fix over there with water or H plus. So now I've balanced all of the mass, all of my elements are balanced. The last thing I need to do is balance the charges, right? Now I know in this half reaction, my electrons are on the reactant side, that's a reduction. So if this is truly an oxidation reduction reaction, my electrons have to go on the right-hand side in the nitrogen, right? So let's check that. My total charge on this side of my reaction, I've got 5 things with a 0 charge and 1 thing with a 0 charge. My total charge on this side is 0. My total charge over here, I've got 2 minus 1s, and I've got 10 plus 1s. 2 times minus 1 plus 10 times plus 1 equals plus 8. So the total charge on the right-hand side is plus 8. So what I need to do is figure out how many electrons I need to add to make both of these sides the same. So I need to bring this charge down by how many units to make it equal to this one. They're 8 units apart, right? So I'm going to add 8 electrons to this equation. If I do that, everything should be balanced. Right? Couple of things that you should notice. There are some tricks that go with this. First off, as I'm going through my steps, whichever side I add water to here, my H plus is always going on the opposite side. The other thing you'll notice is, as you do a bunch of these as practice, because I know you guys are just going to want to do over and over these, just practice them all weekend, right? Usually my electrons go on the same side as the H plus, because when I'm adding my H plus, I'm usually ramping up the positive charge on that side, which means I need to probably bring it back down and make it match the other side, right? So almost always, H plus on the opposite side from water, electrons on the same side as H plus. Just little things that we observe as we do lots of problems of this sort. Right? So, question? All right, so now, the trick is I need to be able to provide exactly as many electrons as I am consuming. So this reaction provides how many electrons? How many electrons are consumed here? 2. So in order to make sure all of my electrons are used up, I'm going to multiply this half reaction by 4. That will allow me to cancel my electrons when I'm done. Okay, so the last step is to combine and simplify. So as I take this particular reaction, I've got 8 electrons plus four Br2s give me 8 Br minuses. And I've got my other half reaction, which has N2O and 5 waters over here. And on the right-hand side, I have 2 nitrates, 10 H pluses, and 8 electrons. The electrons must cancel. If they don't cancel, you've done something wrong. Right? So those are going to go away. Which means my overall balanced equation says my 5 liquid waters are going to interact with 4 liquid bromines and 1 gaseous NO2 to produce 8 bromide ions, 2 nitrogen ions, and release 10 hydrogen ions. There we go. So if I've done this correctly, everything should balance. Questions? Other things to think about. In the examples we've done, this other half reaction over here hasn't necessarily had to go through all the steps. But keep in mind that if this has oxygen or hydrogen in it and I have to be adding water and H plus, right, then I could have waters and H pluses up here that might end up canceling as well. So remember to use your rules about spectators, things that appear on both sides in the same form can be canceled, right? So if you happen to have water or H plus in both half reactions, you might be canceling some of those, more than just canceling electrons. Right? The other thing to keep in mind is that we always write these as net ionic equations, and we don't break up the species as we go into our balanced equation. So I did not take this apart into nitrogen and oxygen. Right? We're balancing them as blocks here. And the same thing is true here. I didn't take my Br2 apart into Brs or anything. So I'm using them as they appear in the equations. Right? Questions about any of that stuff? Good. Many of you have seen these before, I think. It's a lot of steps. They take time to do. Right? But if you're careful in how you do them, it's an algorithm that you follow and you get to the right place pretty much every time. Questions? All right, so why do we do this? In part because we're setting up this idea of how we can utilize oxidation reduction reactions in a useful way, right? The simplest way to think of this is as a battery, right? Batteries are ways that we use oxidation reduction reactions to power other things. We take advantage of the fact that I have one half reaction that's making electrons, another one that's consuming electrons, and I separate those 2 half reactions into 2 different containers. Right? Nobody says that the molecules necessarily have to be in the same place to provide or consume the electrons in those reactions. So we can pick a relatively straightforward oxidation reduction reaction, the reaction of zinc solid with copper ions to give copper solid and zinc ions, is a relatively common demonstration. You can look this up. They got lots of videos for it online, and you can see what's happening in that reaction. We talked about the silver tree last time. It's kind of like this, but a little different. But I have two half reactions where I have a zinc going to zinc 2 plus and 2 electrons. That's providing my electrons, powering my copper reduction, copper becoming copper solid by adding 2 electrons. So here is my oxidation, and here is my reduction. I will not ask you to draw an electrochemical cell on the final, right? We said before that the final will have a disproportionate amount of material, kind of covering the things we've done since exam 3, and then the rest is all the other exams. So we're going to be talking about these, but I won't ask you to draw something like this. This is a crude idea of the starting point for a battery. If you've looked at batteries in the past, maybe in high school or in physics and things like that, all we're really doing is taking the two parts of an oxidation reduction reaction and separating them into different containers and forcing them to communicate through wires, essentially. So if I take my zinc half reaction here, and I connect this zinc solid as part of my oxidation to the copper solid in this other beaker over here, right, with a wire, I provide a path for electrons to move from one side of my reaction to the other. And as a matter of fact, if as soon as you connect this guy right here, if I had a voltmeter in here or something, I could monitor the flow of electrons. But what happens is that the flow of electrons starts at a certain level and drops off almost immediately, and then stops. Right? Because everybody knows that if you have an electrical situation, you've got to have a circuit. Right? You've got to have a way for our charges to balance out. So what's happening? I'm taking negative charges and I'm pushing them over here. I'm building up negative charge over on this side. So if my negative charges are building up over here and I have more electrons that might want to flow in that direction, they're going to be repelled. Right? So we get that initial negative charge over here, which stops the further ones, and we see that our flow of electrons drops off almost immediately. So in just about every battery, you have to have a return circuit, something that allows you to compensate for the charge moving from one side to the other. Usually we think of it as being some kind of a paste or a sludge or something that we call a salt bridge. Right? In essence, we can think of this as being like a supersaturated sludge of potassium nitrate or some other ions that don't participate in your reaction. So what happens is my electrons start to flow in this direction, and I start to build up negative charge, it's going to repel these nitrate ions, which don't participate in the reaction, over to this side. This side's becoming more positive, right? As the electrons flow from left to right, I'm making more zinc plus 2, right? So I need ions to help balance my charge on the left as well. So the negative nitrates go in this direction, and as my negative charge builds up over here, it attracts the positive potassium ions in this potassium nitrate sludge over to the right-hand side, right? And in the end, we get this guy over here. How many people have noticed that, over time, if you have like a remote control or something, you put batteries in it, and eventually the thing doesn't work, and when we pop it open, the batteries are kind of gooped out, you got all this sludge and nasty stuff or whatever? That's this stuff right here, right? Whatever's being used as your salt bridge, over time, is starting to degrade, and then it starts to make gases, and creates pressure, and it pops your battery open, and you get all that sludge coming out. Okay? And of course, it eats up the leads. You've got to buy a new thing, a new remote, or whatever it happens to be. Right? So what's happening? Over time, my zinc is turning to zinc plus 2. It's slowly dissolving on this side of my reaction. Right? My zinc solid is going away. As my reaction continues, I'm making this. Over here, my copper solution is becoming less concentrated because my copper is depositing as copper solid on the surface of the electrode. So my cartoony drawing here shows you that the copper is getting bigger, the zinc is getting smaller over time as this reaction occurs. And essentially, we're going to try to harness the power of this particular reaction by putting something in between the zinc and the copper in that wire that can use the electrons before they get to the other side. Right? That's the basic idea behind how a battery works. Right? We're going to separate our half reactions and try to make use of the electrons before they can get to their destination. Right? Some terminology that we run into, the solid parts in here, the metal strips, we call electrodes. The electrode where the oxidation is occurring, we call the cathode. The electrode where the reduction is occurring, we call the cathode. And those two solutions that we have that are carrying the ions that either form or are being consumed in the oxidation-reduction reaction, the zinc plus 2 or the copper plus 2, we call electrolytes. We talked about electrolytes in Chem 115. It's just a solution of ionic stuff. Right? So we have an electrolyte solution on each side. And again, we said the anode is where the oxidation is happening. That's our zinc. And the cathode is where the reduction is happening. That's our copper. So we have these two reactions. Typically, when we draw a battery, by definition, we try to put the anode on the left and the cathode on the right. So we think of positive flow of electrons as being from left to right in these kinds of reactions. Right? If I took my two electrodes and switched them, and I put the zinc on the right and the copper on the left, naturally the electrons are still flowing from zinc to copper. That would be the equivalent of taking my reaction and flipping it over. So what I've done is I've taken two half reactions and separated them in such a way that I can now talk about this particular battery as a function of those two half reactions. Questions? All right, here come a lot of battery pictures. Right? We can put just about anything we want, like we said in that wire. In this case, I got a little box with a V to represent a voltmeter. Right? That voltmeter is what's actually going to be measuring the force that's pushing the electrons from one side to the other. In a sense, it's going to be measuring how spontaneous that reaction happens to be. We're going to go through a few things before we get to how delta G fits into this. But it's going to be measuring our spontaneity. As our electrons flow from left to right, we take that as the positive direction. A spontaneous reaction then is set up in such a way that I have oxidation on the left and reduction on the right. If my voltage, my potential is negative rather, my electrons are flowing in the opposite direction, it tells me that I've set up my battery backwards compared to the convention. We think of this the same way as delta G. If I have a delta G that gives us a spontaneous process, my electrons or my reaction is going from left to right. If I have a non-spontaneous, or I've written the reaction the wrong way, it's backwards, our reaction wants to go from right to left. Right? So this is all going to start to fit together at some point as we do a little bit more with potentials, that idea of the force that we have pushing our electrons back and forth, and we measure potential in volts. Right? A volt is nothing more than a joule per unit of charge. In this case, remember, a coulomb is the fundamental unit of electrical charge based on electrons. So for every joule that we must use to push a coulomb, that measures 1 volt. So volts are what we're going to be using, in a sense, as a proxy for energy in this particular case, as we measure how our batteries work. Right? We're also then measuring how our electrochemical reactions, our redox reactions, are going as well. Right? So, another thing that we can do is we can define standard conditions and measure the voltage in a standard way. So we use capital E to represent the cell potential or the voltage of our reactions. Right? E naught then is standard conditions, which we remember from equilibrium as being 25 degrees C, 1 molar for solutions, and 1 atmosphere of pressure for gases. All right, what else can we do? What you'll find sometimes is a simplified notation to represent what's going on in an electrochemical cell. So what we do is we use little vertical bars, this way, bars, to separate or represent phase changes. So I can take this reaction where I have my two half reactions, zinc solid turning into zinc 2+, copper 2 plus turning into copper solid, as thinking I'm going to read from left to right across my reaction. I have a solid zinc electrode. I have a vertical bar here that tells me I have a phase change from solid to aqueous. And as I read my way across, I have to go through the salt bridge, that's what this guy represents, to get to copper 2 plus in the aqueous form, and finally a copper electrode. So if I start here and work my way across, that's all that that notation represents. We aren't going to use it a lot. You'll see it in the Gilbert text. I'll reference those pages for people who want to look at that. We're using primarily the Rayner-Canham book for this section. And they use that less because they're more concerned with things like the balanced redox equations we just did and how to use those to determine their spontaneity based on voltages. So, when you encounter that kind of notation, that's what that represents. An electrochemical cell with a zinc electrode and a zinc electrolyte, or this half reaction, becoming this half reaction over here. Can we see how the parts translate? Yes? All right. And again, I'm not going to test you on the battery notation. It's just something you're going to encounter. All right, and you may see it even on the MCAT because they do electrochemical cells on the MCAT. Okay, so in essence, I know I can measure the cell potential, the voltage, what's forcing the electrons to go from one side to another if I put that voltmeter in there. And what I discover is that my electrons are being pushed with a potential, joules per coulomb, of 1.1 volts. All right, so what does that mean? Well, a volt is still kind of a nebulous term for us, right? But what it does is it tells us how much force, again, what energy is required to move a unit of charge across this battery. And it says the way I have my battery set up, I have it set up the right way. My electrons want to flow from zinc to copper. And that I can measure that force pushing it as being 1.1 volts. It's a little different from delta G because we know delta G is negative for spontaneous processes. We're going to come back to why or how these things fit together again in a few minutes. But I can measure this particular cell in this way. Right? Let's look at something a little bit different. Again, this is the parade of electrochemical cells. Suppose I replace my copper with something like silver. And I measure how much force is pushing those electrons from one side to another. Right? What I notice is that the electrons are being pushed with a much greater force, 1.5 volts, in this case 1.56, as compared to 1.1. So it says that when I put silver over there, the oxidation of zinc coupled to the reduction of silver is a more spontaneous reaction than the one that I had for zinc and copper. This is in part why we run into things like copper and silver and eventually gold. Gold is even more spontaneous yet in jewelry, right? Because we know that those things tend to want to be solids, they don't want to be ions. Right? And we don't have to worry about then if I stick my hand with the gold ring into a solution that has ions in it, I don't have to worry about it spontaneously dissolving or getting an electrical shock. Because it's already in the form it wants to be in. All right, so here's this one. What you should notice is that copper and silver are separated by about 0.46 volts. Right? So it should make sense that if I built an electrochemical cell that had copper and silver in it, I should be able to measure that. And in fact, it turns out to be exactly the same. So what I'm actually measuring here is a state function. It's a function of delta G, which we'll talk about again in a few minutes, I keep saying. Right? It's an energy diagram expressed in volts. So what I'm doing is really separating a whole bunch of different energy states based on how I measure their voltages. And I can measure any one of them relative to the other just by taking them, building a battery, and plugging in my electrodes and figuring out what the cell potential is. Now, this is a lot like what we did with delta H. right? I'm talking about differences between energy levels, right? Energy levels measured in volts. But I don't know what their absolute numbers happen to be. So when I did delta H, what did I do? I established a reference. For delta H, my reference is elements in their standard states. Well, the problem we have here is all our elements are very different, and they function in very different ways. So we just pick one. We pick one element in particular to be our standard, and that's the reduction of hydrogen ions to form water, right? Or sorry, to form H2, right? What we call the standard hydrogen electrode, right? And we make the reduction of that relative to the other elements equal to 0. Right? So all we're really doing is dropping a 0 point into our relative energy diagram and measuring relative to this. Based on this, zinc and zinc plus 2 are on the negative side of 0, right? They're below, and they're pushing electrons up. Copper and silver are on the positive side. What does this tell us? Well, it gives us some idea about how reactions want to occur. Zinc wants to give away electrons. Zinc wants to be a reductant, right? It wants to give away electrons. In essence, what happens is if I dissolve zinc, or if I put zinc in acid, it's going to dissolve and turn into zinc ions, and I'm going to make hydrogen gas. We observed this back in Chem 115 when we took pennies and we dissolved them, right? The core of that penny was made out of zinc. The outer shell was made out of copper. We threw it in nitric acid, and we were able to dissolve the penny, right? Because the zinc goes away. Lots of fizzing, lots of stuff like that. That's mostly hydrogen being produced. If I take copper or silver, because they are on the side that wants to receive electrons, and I put them in acid, H plus doesn't have a source of electrons really. My copper or zinc don't want to dissolve. They want to stay in the solid state. They are things that don't corrode very effectively. And as a result, like we said, they're great for jewelry. We use copper for pipes. You know, all of these different things where we don't want them to corrode and fall apart easily. Those are great applications for things like that. Lead, it actually turns out, is right there next to hydrogen ion. And as a result, it's great for doing lots of other things too, like making pipes and stuff. Right? Fortunately, it's pretty toxic. Right? So we have to find better alternatives. But basically what this diagram tells us is, relative to hydrogen, right, if I'm above that, metals want to be in their solid form. If I'm below it, those things tend to want to give electrons to hydrogen and dissolve. Right? In your textbook you'll see what they call the activity series of metals. That's all it really says. Anything below hydrogen, below 0, on our stuff is going to dissolve in acid. Anything above that doesn't want to dissolve in acid. Matter of fact, we had to go to pretty heroic measures to make our copper pennies dissolve. We had to add pretty concentrated nitric acid in order to make that work. Right? There's more things going on in there than just H plus. All right. So if I have a 0 point, I can reorganize my diagram. Right? Instead of measuring everything relative to zinc, like we just did, I can measure things relative to my hydrogen ion. Now here's part of the problem. Hydrogen is a gas, so it's hard to make an electrode out of a gas, so what do? Right? We basically have a big hollow tube with what we call a non-participating electrode, something like platinum, right? A metal that does not corrode very well, as our electron carrier. And then we can measure how our hydrogen, so I have a mixture as I go from my electrode, platinum, to hydrogen gas, H plus. Those are my phase changes. Again, don't worry about the diagram so much, but rather than just telling you how you're getting from one place to the next. And now I can measure just about everything, right? I know that my copper is 0.34 volts above acid. If I put copper over here, I should see that the cell potential, the voltage, is 0.34 volts. If I put silver over here, like I do here, and I measure this, I should get 0.34 plus 0.46, 0.80 volts. So I now have a standard way to measure my electrochemical reactions based on hydrogen. When we did this with delta H and delta G, we said now we can just tabulate all the stuff we're interested in and do a subtraction and get the information we want. And that's what's going to happen here. Now that I've got relative values based on hydrogen, right, I can go through and I can measure the potential of an electrochemical reaction, how much force is pushing the electrons, just by looking at the two half reactions. Where am I? And they're all relative, measured relative to hydrogen. All right, so how do we do that? Well, typically, when we measure the potential of our battery, we look at the positive or the higher number and subtract the bottom number in order to figure out how far apart they are. Right? That's essentially what we did. Right? So what we do is we say then, fine, on the right-hand side of my battery is where my reduction should be happening. Right? And on the left-hand side of my battery is where my oxidation should be happening. So if I know my half reactions and I know their potentials, I can separate the reduction and oxidation and subtract the oxidation from that and figure out how far apart they are. That's all these equations tell us to do. So let's look at an example. Here's an oxidation reduction reaction that we can balance by the half reaction method. And I can figure out what's going on by separating them into their parts. I know that manganese O2, MnO2 on the left, is becoming MnO4 minus. And I know that my sulfate is becoming SO2. It's a little different from looking at metals. But for any oxidation reduction reaction, I can take the two parts and separate the oxidation into one side and put the reduction on the other side. Right? So it doesn't have to just be metals. I can do anything this way. So if I know what the oxidation is and what the reduction is, all I have to do is figure out what their relative potentials are. So if you have a big table of values that tell us voltages, that tell us potentials, we can calculate what our overall potential for this reaction happens to be. So here's MnO2 reacting with SO4 to become SO2 and MnO4 minus. If I look at my table, all I have to do is find a half reaction that has my two reacting species in it. And as I work my way down, I find, look, there's manganese and MnO2 in one half reaction. It doesn't matter the order that they're put in because all of our values are written relative to hydrogen, which means they're all written as reductions. So it doesn't matter that my MnO4 is on the left and my MnO2 is on the right. We're just looking for something that has both those species in it. So it tells me that this particular reaction right here has a potential of positive 0.59 volts. My other half reaction, sulfite and SO2, I can find in the green, positive 0.20 volts. So now all I have to do is take my oxidation and reduction, and I can find E for the reaction, the potential that moves the electrons, by taking E0 of my reduction and subtracting E0 of my oxidation. Okay, so now the question is, which one is my reduction? Well, my reduction is sulfate, with sulfur going from the +6 state, oxidation state, to sulfur in the +4 oxidation state. There's my reduction. So I can plug in that voltage right here. My oxidation is manganese going from the +4 state to manganese going to the +7 state. That's my oxidation. So I'm going to subtract positive 0.59 volts here. I get a final value of 0.39 volts in the negative direction. Now, if we look at our potentials, what do I see? I see manganese is above sulfate. In this particular process, I'm trying to push, as my reaction is written, electrons from manganese to sulfur. But manganese is higher on the list. I'm making the electrons go the wrong way, and that's reflected in my potential there. It says I'm getting a negative value, which means my reaction is written backwards. or that this is a non-spontaneous reaction. Spontaneous in the reverse direction. Questions? So as long as I can separate any oxidation reduction half reaction into half reactions, and I have a big ass table of potentials here, probably only the third or fourth time I've said big ass all term long, but there you go, just on your way out the door. I can calculate that potential that's moving the electrons. Go ahead.
Why don't you have to flip the value since that's a reduction?
Because the negative sign does that for us, right? So if I wanted to figure out how far it was from one point to another, and I have stopping points in between, like the standard hydrogen electrode, I would just add the distances together, right? But since my oxidation, by definition, is going the opposite direction, I put a negative sign in here and it accomplishes the same thing. Does that make sense? So we don't have to flip the potentials because that's already done for you in that reaction. I recognize that if you did this in high school, maybe in a physics class or earth science or even chemistry, you may have seen the reaction written the other way where it's plus the negative of the oxidation. Plus the negative is the same thing as subtraction. Other questions? So all we have to do is take our reaction, figure out what the half reactions are, and move them from one place to the next. All right. How does this fit in with spontaneity? Well, I've already been hinting that a positive potential, a positive voltage, means that I have a spontaneous reaction. And a negative voltage means that I have a non-spontaneous reaction. Right? Well, that means then that delta G and cell potentials, right, delta G and the voltage itself must be related by the negative. So as I calculate things like this, keeping in mind delta G came long after we had any idea how to measure cell potentials or anything like that. We knew about voltages long before we knew about delta G. We're making delta G fit the conventions that we have for our batteries rather than the other way around. That's why we've got to modify this. All right, so the thing about potentials, as we've talked about these, is we haven't talked about reactions the same way we talked about delta H and delta G. Remember, for delta H and delta G, you had to multiply all the different parts by however many were in the balanced equation, and you add them up and subtract the products and all that kind of good stuff, right? We haven't done any of that here. We just dealt directly with measured voltages. Part of what makes electrochemistry very different from the other things we've done is that it's not until the very end that we really care about how large the reaction is, right? As long as I have 1 molar solutions of all my stuff and my standard states are observed, I can have a battery the size of 2 little beakers like this, or I could have 2 batteries made out of swimming pool size stuff. As long as my contents have the same concentrations and whatever, the voltages are going to be the same. Whereas if I said I have a small container of hydrogen gas here and a large container of hydrogen gas here, they contain very different amounts of potential energy, delta H, right? And we have to figure out how much is in there in order to do that calculation, how much energy, right? So we have to do something to modify our cell potentials to make them relative to delta G, right? First off, we have to get them onto the molar scale. E naught, or the cell potential itself, really is kind of measured on the scale of electrons, right? When we talked about what a volt was, 1 volt is equal to 1 joule per coulomb of charge that we move. And coulombs are measured fundamentally on the level of individual electrons. So one thing we have to do is modify our relationship to get it back to the molar level. That's the Faraday constant, F. Right? The Faraday constant, F, is nothing more than the charge of a single electron times Avogadro's number. So 1.609 times 10 to the negative 19 times 6.022 times 10 to the 23rd gives us 96,485 coulombs per volt electron. A constant that will be on your equations and constants page. It's the only F there, and hopefully when you're done with your exam, it will still be the only F on your exam. Right? So, that's the Faraday constant. N, on the other hand, N is almost always referred or reserved for talking about the number of moles. This is what now allows us to take a process where we don't care about coefficients and make it now related to something like delta G, where we do. N is the number of moles of electrons that we must move in a balanced chemical process. If I look at this reaction right here, N is equal to 2. I have to move 2 moles of electrons in that balanced equation in order to make that reaction work. So if I want to take this particular process right here and calculate what my delta G is for this reaction, where E naught, remember, was positive 1.10 volts. Just like I've accidentally memorized Ka for acetic acid and Kb for ammonia, because we use it all the time. This is the example we use all the time. And so on my tombstone it will say, Dr. Dobke, may he rest in peace, Ka of acetic acid equals this, K whatever. I know that potential of it. There's my E naught. My number of moles of electrons here is 2. And the Faraday constant is always a constant 96,485 coulombs per mole of electrons. So if I take these values, I can calculate delta G for this reaction right here. Delta G is always equal to negative number of moles, 2 moles of electrons, times the Faraday constant, 96,485 coulombs per mole of electrons, times my measured cell potential, right? Positive, and I gotta keep the sign is important, 1.10 volts. Remembering that a volt is a joule per coulomb. This is what makes my units work out. Because in the end, I have to have units of energy. Right? I have to end up in joules in some way. So my moles of electrons cancel here, my coulombs go away here, and I'm left with joules. Question? This is going to be a big number because whatever I'm multiplying by has got 96,485 in it. What is delta G of my reaction?
-212.267 kilojoules.
212 point what?
267.
All right. Remember that 2 moles of electron is exact, right? So it has infinite significant figures. I can't have 2.3 electrons. There's no such thing as 0.3 electrons, correct? So it's 2 with zeros forever and ever. 5 sig figs there. I got 3 here. I get 3 in my answer. There's a number we're used to seeing, right? We're used to dealing with numbers in terms of kilojoules. Spontaneous. We've set up our battery in the right direction. It's going the correct way. Questions about that? All right. Suppose we look at this reaction right here. Here's an electrochemical cell setup that tells you pretty much right off the bat which part is which. Right? It tells us what our reduction is, what our oxidation is, and it actually tells you what the cell potential is. The thing that we often struggle with is figuring out how many moles of electrons we need to move from one side to another. Right? So as I look at this particular reaction, when I separate this into half reactions, I've got copper. It's not going to copper solid, it's just going to copper plus 1. And over here I've got manganese going to manganese 2 plus. So when I set this up, and I think about how many electrons have to move, my copper is only changing by 1 electron. In this case, I don't need the half reaction method to figure out what my individual values happen to be. I can just plug in electrons to make these work. There's no oxygen or hydrogen or anything in here. But this guy has to happen twice. So the number of moles of electrons that I have to move in the balanced equation is 2. Make sense? Okay. So when I calculate delta G for this reaction, my N, 2 moles of electron, turns out to be something that looks very familiar. I'm just going to change the potential here. In this case, my measured potential positive 1.3 volts. So this is a reaction. Because it's positive, we know delta G should be negative, very spontaneous, more spontaneous than that reaction here. Go ahead.
When you calculate like the E naught,
Mhm.
when you do like the cathode minus anode, will you double, like if it's in here, will you double?
No. All we do is, and this is the thing that makes cell potential, this is my least favorite portion of the course, because it's the least intuitive. Batteries are cool, I get that part. But it's the least intuitive because the calculation of the E zeros, the E naughts for this process is independent of size. Right? Like I said before, if I have standard conditions, all those are met. The potential difference, the voltage moving electrons from a reaction, a battery that's this big, where I'm working 2 beakers versus swimming pool size solutions is exactly the same. So the size of the reaction is immaterial to the force that pushes the electrons from one side to the other. Which is why we need to make this adjustment at the end in order to get to something like delta G that depends on how big their individual things are. Does that make sense? Okay. So we can do this one. This one is going to be about, 25% bigger than that, about negative 250 kilojoules or so.
Negative 57.
Negative 257. Spontaneous. Question? Okay. So now we have a new way to calculate delta G. We've got like 5 now. Where did we get there? Oh, where'd it go? Oh, I lost it. All of my different delta G terms. Okay, I must have taken it out. You guys don't pay enough money to get quality instruction. All I have is more examples. Right, so here's an example we did the other day, right? Something like this anyway, where we took manganese and reduced it using iron. Again, finding that number of electrons tends to be the hardest part of doing these chemical calculations on electrochemistry. Right? So here were the 2 balanced half reactions we ended up with on Monday. You can refer back to that. The N is going to come from the number of electrons that we cancel, right? So I needed 3 electrons to make that process work. I needed 3 irons. So that's what I'm looking for, right? When I have numbers that are not necessarily 1 and something else, so let's say maybe I have 2 in one half reaction and 3 in the other, right? Since I can't have partial electrons, I'm going to end up with 6. Does that make sense? I have to make 2 electrons 3 times. I have to consume 3 electrons twice in order to make all the electrons go away. That's the number you're going to end up looking for. What am I canceling out at the end down here? Right? If you're doing one of these longer ones. So in this particular process, in order to figure out, boy, I suck. Where are we? Let's go back here. In order to calculate delta O for this, or delta G for this reaction, my delta G is going to be equal to negative 3 moles of electrons, 96,485. Right, I have to jump around a little bit because I'm just not planning on like this. Coulombs per mole. I need my cell potentials, right? So my 2 half reactions. Play a little song. My 2 half reactions, there we go, are manganese, permanganate going to MnO2, and iron plus 2 going to iron plus 3. Which one is the oxidation? It's the iron, right? So I'm going to need to calculate E0 of the reduction minus E0 of the oxidation. The oxidation is iron plus 2 and iron plus 3. And my reduction then is MnO4 minus and MnO2. So those are the half reactions I'm looking for in my table. Right? All right, let's see if I can find them. Well, in order to calculate that change in potential, I'm looking for, there's MnO4 and MnO2 right there. That's 0.59 volts. So I can plug that value in. Positive. Subtract iron plus 2, iron plus 3. Where is that?
There it is, right there.
Positive 0.77 volts. Is that?
Is that even multiplied by
No, we don't multiply them by 3, we did that here. Right, so again, when we calculate the difference between the levels, how far apart they are, E0 doesn't care about the size. Right? But in order to get to delta G, we need to introduce scale. Right? How many times does this reaction happen in order to make it work? All right, negative 3 moles of electrons, 96,485 coulombs per mole of electrons, times negative 0.18 volts. Right? So it tells us this particular reaction is going to be non-spontaneous, right? The potential, the voltage is negative. A negative times a negative means delta G is positive, non-spontaneous. And it's not going to be a very big number, right, in terms of kilojoules, because this number is fairly small. What do I get for a value for this one?
52.1.
All right, 2 sig figs, because I'm limited by that one. Questions about doing all this stuff? So it's identifying an oxidation and reduction, finding them on the table, plugging in their numbers and getting the difference. And then I have to find the number of electrons to get delta G. All right, the last part that we're going to bring this to is this whole idea of how we calculate non-standard potentials. What happens when we get away from 1 molar solutions and such. All right. We can calculate that by linking delta G in one form, negative NFE, to delta G in another form, negative RTLNK. Right? Put your pencils down. You're not going to get tested on this. This is what the different values of delta G allow us to do. This is what you've done in lab, right? You use delta G in different forms to calculate delta H and delta S for borax, right? You've used delta G in different forms to calculate EA, right? The activation energy for a reaction. Here, we can use delta G in different forms to figure out how a battery changes in its ability to provide or consume electrons with concentration. So K, or if you prefer Q, because once we get away from standard conditions, right, or from equilibrium, K can't be K, it has to be something else, provides a ratio of concentrations that allows us to see what happens to our potential. What you'll notice is that this looks an awful lot like the Henderson-Hasselbalch equation, doesn't it? What it says is I have a starting point, E naught for my cell, negative 0.18 volts, right? Positive 1.1 volts, right? And then as the concentrations change, which are hidden in Q, right? Remember Q looks like K. As the concentrations change, I'm going to adjust my potential based on those values. And in order to do that, I have to keep in mind I've got N and F and all those other things. We're just modifying the value based on changing concentrations. This is how we calculate this. It's called the Nernst equation. Nernst is a particularly funny sounding name. So it's probably someone who was teased a lot as a child. But he came up with this relationship that allows us to take these two values, or these different values, and modify them based on concentrations. Right? I introduced this here because it will come back. It'll come back in PCAM. You may or may not see it. I don't know if they actually talk about this on the MCAT anymore or anything like that. But the Nernst equation is how we make these modifications. We can rewrite it in terms of an LOG log instead of an LN log. That's the form that we see more often. And if our temperature happens to be 25 degrees C, then we end up with a whole bunch of constants and the number of electrons that we're moving, right? So that's the form we run into more often than not, the value on the right-hand side. Just showing it to you because if I don't, then I'm doing you a disservice. Have we had enough? Are our brains full for the term? Right? Or if they're not quite full, you're just going to say, yeah, they are, and they'll just go, oh. Kind of like when your mom says, you're feeling